For section 3 of chapter 8, we look at the hypothesis testing process when the population standard deviation is unknown using a t-test. So much like in chapter 7, when we were constructing a confidence interval for the population mean when the standard deviation was unknown, and we had to estimate that using S, the sample standard deviation, it's a very similar process in section 8.3 when we look at hypothesis testing. For the t-test, the t-test is a statistical test just like the z-test was in the previous section, and we're only primarily focused on a mean for right now. We're not going to look at a proportion or a test for standard deviation or variance. But the t-test is for when the population is normally distributed, or it could be approximately normal, and also when the standard deviation of the population is unknown, and we have to use S, the sample standard deviation, to estimate it. The formula for a t-test, which is the test value, is very similar to the formula for a z-test for the test value, except we use t, so x bar minus mu divided by s, which is divided by the square root of n. So we've seen this formula before, and then we incorporate back again degrees of freedom that we talked about in chapter 7 with the confidence interval, because we are estimating one of the values and we're allowing that value to be fixed and the other values to vary in the sample data. The 5-step hypothesis process is very similar to the traditional method. We still state our hypotheses, so there's still 2 hypotheses. You have the null hypothesis, which is still no difference, so the average will always equal a certain value. And the alternative hypothesis is that there is no difference, or that there is a difference, and we're trying to determine what that difference is, if it's less, if it's more, if it's either. The critical value, what we just, well, not what we just looked at, but the critical value comes from table F, and to find the critical value, it's much similar to finding the critical value when we did the confidence interval. We look at, well, we need the alpha value, so that's being given just like it was with the z-test from the previous section. We also need to know, is it a one-tailed or a two-tailed test like we talked about previously, and then we also need to be able to find the degrees of freedom. So that's the information we need in order to find the critical value, and we'll refresh our memories on that as well. The test value is the formula we looked at previously, so it's a t-score essentially, which is x bar sample mean minus population mean divided by sample standard deviation divided by the square root of n. Our decision more or less will be very similar to the decision you made with the traditional method. Given a certain critical value that we get from table F, you create a distribution. The region you shade in will be based on the alternative hypothesis. So this particular example would be a right tail test because of the greater than symbol. So the area in the tail is going to be based on that. And then that's considered our critical region, or AKA the rejection region. And so we look at our test value and determine, is that test value in the critical region? So we would reject the null hypothesis, or is that test value outside of the critical region and we do not reject the null hypothesis. So more or less, we look at the same steps for 8.3. We just have an additional process, which is we need to estimate the standard deviation with S, sample standard deviation, and then we also use a different table to find our critical value than we did in section 8.2. So let's look at an example. We have 3 examples to kind of represent the 3 different types of tests you can do. 2 one-tailed and 1 two-tailed. So for this one, we talk about cigarette smoking. A researcher found that a cigarette smoker smokes on average 31 cigarettes a day. She feels that this average is too high. She selected a random sample of 10 smokers and found that the mean number of cigarettes they smoked per day was 28. The sample standard deviation was 2.8, so that's 2.8 cigarettes per day. At alpha equals 0.05, is there enough evidence to support her claim? And then we look at, well, there's certain information that we want to be able to identify every time, and that would be the population average, so the 31, the sample size, which is the 10 people, the mean of that sample, which is the 28, and then the sample standard deviation. So this time, instead of us having sigma, which is kind of like the little fancy O that we've been looking at, which is the population standard deviation, we have the sample standard deviation that was given, which is 2.7. So that information lets us know that because we're given this information, or if we ever have to find it, then we're going to do a t-test instead of a z-test. for the hypothesis test. We know that our alpha value is 0.05, and then we'll talk about what type of test it is after we do the first couple of steps. So our first step is remains the same regardless if it's traditional, p-value, or now this particular method. For a t-test, it state our hypotheses, which our null hypothesis is that there's no difference in the average. So the true mean number of smokers, or the true mean number of cigarettes per day for a smoker is 31. But she felt like that average is too high. So the alternative hypothesis must mean that the mean number is less than 31. And this particular value would be our claim, because it's not stated that something else is the claim in the problem. Like in section 8 point, in the beginning with 8.2, it was stated in there that one of the problems had actually said, hey, this is the claim. But since this one does not come out and say that, our alternative hypothesis is always going to be the claim unless otherwise stated in the problem. So now that we've written our hypotheses, we look at, well, what is our critical value? So to find the critical value, we're going to use table F, because we do not know the population standard deviation. To utilize table F, just to review this, we need to know degrees of freedom. We need to know if it is a one-tailed or a two-tailed test. We no longer really care about confidence interval because that was chapter 7, so we kind of ignore that. So as long as we know degrees of freedom, and we know one-tailed or two-tailed, and then we know the value of alpha, we can find our critical value, because these are the critical values here in the table. So we know that the degrees of freedom is the sample size minus 1. So 10 minus 1 is 9. My alpha is 0.05. And this is a one-tailed test. Now, I know it's one-tailed because of the symbol here, less than. It's only on the left side of the distribution. So when I go look at my table, I'm looking for one-tailed, 0.05 for alpha, and also 9 for degrees of freedom. So we want one-tailed, 0.05 for alpha, and I want to go down and I want to find 9, and it's 1.833. Now this distribution, if you recall from chapter 7, has similar characteristics as table F, which is a standard normal distribution. And these values are either positive or negative, so it depends on the type of test we're doing. This is essentially a left-tailed test. So even though we know the area is on the left and we expect a negative z-score in the table, it will always be reflected as positive. We have to just make sure we use a negative value. So my critical value here will be 1.833, but negative. And that is solely because of the alternative hypothesis, because it says less than. And then we calculate our test value. So the average minus the sample average minus the population average divided by the sample standard deviation, which that's divided by the square root of n. We get negative 3.51. And then we end up comparing this value to this value. So with our fourth step, we look at making our decision. And for that, I'm going to draw the distribution. Since the t-distribution has the same characteristics as the standard normal distribution. So this is my normal curve. This is my critical value, which is what I mark off on the distribution. And then I shade everything to the left because of my alternative hypothesis. And I determine, well, where is this value in relation to this, to the decision I'm going to make? Is that value in the critical region, or is that value outside of the critical region? In this case, it's far into the critical region, which tells us that we can safely reject the null hypothesis. You know, that's the decision that we've talked about previously, that if the test value is inside the critical region, then that lets us know that we need to reject the null hypothesis. Then once we have our decision, we just have to summarize that. In the question, it says, is there evidence to support her claim? Well, this was the claim that the average was too high. So by default, we said that the average was less than 31. And since we are rejecting the null hypothesis, which that there's no difference in the averages, that there is evidence to support the claim. So when we do our little summary, there is sufficient evidence to support the claim that the average number of cigarettes that a smoker smokes per day is 31, or is less than 31. So we want to just be able to kind of formalize that in words. I know in your homework, you just have a little drop down that you select. Either there is sufficient, or I believe it's is sufficient or is not sufficient. Or maybe it's just the words is or not. But you really not writing out a full statement. You are been able to choose what verbiage, what's the correct wording that goes in that based on your decision. And also we have to make sure we get the claim right. So the claim is generally always the alternative hypothesis unless otherwise stated in the problem. So we'll look at an example of that here coming up. All right, so let's look at another example. Here we have the heights of tall buildings. So a researcher estimates that the average height of buildings of 30 or more stories in a large city is at least 700 feet. A random sample of 10 buildings is selected and the heights in feet are shown. So these are the heights. At alpha equals 0.025, is there enough evidence to reject the claim? So we want to make sure that we identify all the key information, mainly those 5 components that we've talked about each time we've began the hypothesis testing, especially with the section 8.1. And this is actually, let me fix that. This is actually 8.3, not 8.2. So actually like a little 3 there. However, we want to be able to either obtain information from the problem or use the data provided to get the information that we need. So we know we need the population average. In that case, is 700 feet, right? It says the researcher estimates that the average height of buildings of 30 or more stories in a large city is at least 700 feet. So that at least means it's either 700 feet or higher. So we just use this value for our average. And then we know the sample size is 10, and we have to find the average of that. So we add all these values together, and we get 6,065 divided by 10. So the average height from our sample is 606.5 feet. Now we have to also find because in the problem is nowhere it mentions standard deviation. So we have to find that value ourselves. And just kind of a reminder of the formula. This is a formula that you were first kind of used in chapter 3, I think section 3, which is the measures of variation, measures of spread. And you also used this formula for the confidence intervals as well when you looked at a t-interval when sigma was unknown. So more or less it's the same. If you have data and you have to do a t-test, like you did a t-interval, then you have to find that standard deviation. So I've written the formula here. N would be 10. The sum of x squared will be taking each one of these values, 45 squared, 520 squared, and so on, finding the sum. This sum of x is the 6,065. Have to square that, and then do 10 times 9, and then evaluate that, take the square root, and you'll get the standard deviation. So 109.1 feet is my standard deviation. And then we want to be able to conduct our 5 steps. So first step, always the same. What is the hypotheses? So there's no statistical difference in the height. So we would say for the null hypothesis that the mean height for all buildings is equal to 700 feet. Whereas the alternative height, now because she's saying at least 700 feet, it means 700 feet or more. Then we could say for the alternative hypothesis that we expect the mean height to be greater than 700 feet. At least it's kind of like that's the threshold starts at 700 and then it can be any height larger. And then that more or less would be our claim. For our critical value, well, that's where we have to make sure that we know what are the degrees of freedom, what's the alpha level, and then also what type of test are we doing. So in this case, our degrees of freedom are 9. Alpha is 0.025, and this is a one-tailed test because of the symbol here, which is greater than. Or we can look at a right-tailed test. But you already see the critical value here. But I'm going to go to the table and show you. We have a degree of freedom of 9 because it was 10 minus 1. We have a one-tailed test at 0.025, so where they meet up is at 2.262, and we would use a positive 2.262 because of the type of test, with it being the area or to the right of the mean which is greater than 0 for the standard normal distribution, which is more or less like the t-distribution. So steps 1 and 2, very similar to when we first talked about hypothesis testing for the traditional method. Step 3, what is our test value? What value am I using to compare to the critical value to determine the statistical significance? So our sample mean minus population mean divided by sample standard deviation divided by the square root of the sample size, we get negative 2.71. Step 4, if I draw out my distribution, I'm going to find this on my t-distribution, which looks very similar to a normal distribution. Shade in the area greater than, and then I have to determine where is my test value. Is it within that critical region, or is it outside of the critical region? It's very far outside of the critical region, and we know that if it's not in the shaded area, then we will not reject the null hypothesis. So essentially, in this case, the researcher might go through and really would need to reevaluate the alternative hypothesis, because of the sample of 10, the average was far less than she was wanting. So either she would need to reevaluate this and maybe say at most 700 feet, because that would mean 700 feet or less, and then recalculate that information, or take other samples of size 10, or maybe samples of size 30, or samples of size 50, so she can get a better accurate of the estimated average height of these buildings. Because this particular test value is far more lower than the critical value. So that would either indicate that maybe the sampling or the data is not really sufficient enough. You don't want it to be, I would just say it wouldn't be sufficient enough. Either a larger sample size or reevaluate that. But for this problem, we just need to be able to at least do these parts. And then that drives our summary or our conclusion. So the question, is there enough evidence to reject the claim? Well, since we do not reject the null hypothesis, so essentially there is no difference in the mean height of buildings 30 stories or more, then yes, there is enough evidence to reject this claim that the mean height is greater than 700. So we could say there is not sufficient evidence to support the claim that the mean height, or the researchers claim that buildings with 30 or more stories is at least 700 feet tall. And for our last example, we look at average family size. So the average size of a family was reported as 3.8, or 3.8 family members. A random sample of families in a particular school district resulted in the following sizes. So these 24 values at alpha equals 0.05. Does the average size of the family differ from the national average? So with that, still want to be able to identify the important information. So the population average, 3.18. The sample size, we have to count these values and we get 24. The sample mean, if you add all those numbers together and divide by 24, so you get 3.83. And then I've calculated this already. I'm not going to write the formula again, but I've calculated it, calculated the value, 1.43. So this is the information I need to be able to successfully, mainly we need this information, one, to calculate the test statistic, but also our as long as we can identify the population average, then this value here is always our null hypothesis. There's no difference in the averages and in the means. So my null hypothesis is that the average family size is truly 3.18 versus, we wonder, is it really different from that? So if it's different, that means it's not equal to. It could be greater, it could be less, we're just not sure. We just know it's not that number. So for the alternative hypothesis, it's mu equals 3.18. And then they don't mention anywhere in here about claim, so this essentially would be our claim for this problem. And then we find our critical value. So degrees of freedom, 24 minus 1, which is 23, alpha 0.05, and this is a two-tailed test because of it's not equal to. So when I go to my table, I'll look for degrees of freedom of 23. Here we go, 23. And then I want a two-tailed test, and I want 0.05, which is right here. So where they meet up will be 2.069. So go back and 2.069. Now, since it's a two-tailed test, that means my test value or my critical value is actually plus or minus 2.069. And when we do the step 4, I'll show you what I mean. So my test value, use this information here, 3.83 minus 3.18 divided by 1.43, which is divided by the square root of 24. And we get 2.23 for our test value. So for my decision part, I look at, well, I already know that for a two-tailed test, that means we have two critical regions, and they're based on this number, the positive and the negative value. So we have plus and minus 2.069. And then I want to determine, well, is this in either critical region? Should I reject? Or is it outside the critical region and I do not reject it? So that number is inside the critical region. It's here greater than 2.069. And mainly we do a two-tailed test when we're just unsure of the relationship, if it's more or less. If another random sample of 24 families was taken and the average could be less than this number, so then we would get a test value over here on the negative side. And that just tells me to reject the null hypothesis. So when we do our summary, does the average family size differ from the national average? Well, since we are rejecting this, at least for this particular school district, that would be yes, the average family size does differ from the national average. So essentially, although this is the national average, our null hypothesis is saying there is no difference in the true mean from the national average in this particular school versus it's the true family size of this particular school not equal to the national average. In this case, we could say yes to this. Does the average family size differ from that? Yes, that's true based on our results here. And then we just summarize that. So there is sufficient evidence to support the claim that the average family size is different or does differ from the national average. And with that sums up or covers all of our hypothesis testing for chapter 8. This is actually section 8.3, not 8.2. So just make a little correction there. And more or less how to do the hypothesis tests are the same 5 steps as a traditional method. The only difference is you may or may not have to find S, which is the sample standard deviation, and each time you use table F instead of table E, which is the standard normal table.